Okay, so this chapter is about motion in a circle. So a particle will move in a circle, for example. So first of all, we have to know about radians. So radians is the angle actually. So you can see here, radian. 1 radian is the angle subtended at the center of the circle by an arc of length equal to the radius of the circle. So it is the explanation on the meaning of 1 radian. So 1 radian is where the radius has the same length with the arc. So as you can see here, arc length is equal to radius. So when this happens, the angle here is 1 radian. So 1 radian is actually 50 something degree. 50 something degree. Okay, so let's move on. That is the angle part. Okay, so this angle, we call it theta. We call it theta. So we call it theta. So the angle of in radian, we call it theta. Okay, now let's look at the next point. Angular displacement. Angular displacement is the angle through which an object moves through a circle. Okay, so which means angular displacement is actually the theta. It's actually the theta. That means it's the angle. How much angle an object moves through in a circle. Okay, so we have this formula. I think you are familiar with this formula. S equal to R theta. So where we learned this in maths last time. So S equal to R theta. So the angular displacement is actually the theta. So this is the angular displacement. It is angle in radian. Okay, angle in radian, and R is the radius of the circle, and S is the arc length. So I just write down first. S is arc length, and sometimes it is known as linear displacement as well. Linear displacement. Okay, so make sure you know about angular displacement and linear displacement in this way. So angular displacement, right? The unit is radian. Linear displacement, the unit is meter, for example. So that is the main difference between angular displacement and linear displacement. Linear displacement is the displacement that we learned before this. Okay? It's just the normal displacement where it is a distance with direction. So the unit is meter. Angular displacement is the angle. So that's why the unit is radian. Now let's move on. 1.2. Angular velocity. So angular velocity is the rate of change of the angular position of an object as it moves along a curved path. So that means what? That means how fast the angular displacement happens. Okay, so displacement and velocity is related in this way, where displacement divided by time, you get velocity. So likewise, over here, angular displacement, which is theta, you divide by time, then you get angular velocity. So that's why we have this formula here. This formula, they use this special symbol which looks like W, but this is actually omega. Omega. So omega is the symbol for angular velocity, and so omega is equal to theta over time. Okay, so that means you take your angular displacement, you divide by time, then you get angular velocity. So this is a formula. And how about the unit of angular velocity? We have to know about that also. So the unit is, logically, you should be able to think of the unit is radian per second. As you can see the formula, we have theta, which take the unit of radian, and we have time, which take the unit of second. So hence, radian per second. Okay, radian per second. That means something like in 1 second, how much angle in radian does the object take? It's something like that. Now we look at the next point, period. The time taken by the body to complete the circular path once. So it means to make one circle, how much time is spent. So that is period. Period. So the symbol for period is capital T. Capital T. So where you can see the formula here, they are using this formula, omega equal to theta over T. Yeah. Okay. So and they replace theta with 2 pi. 2 pi means one circle. So an object is moving one circle. Imagine that. An object is moving one circle. So the angle is hence 2 pi. And the T at the bottom is capital T. So that is period. So it means the object is moving one complete circle and the time it takes is a period. Okay, so 2 pi over T. Yeah. So this is an example on how we apply the formula just now. How we apply this formula, where we put theta with 2 pi, we put the time with period, then we get angular velocity also. And 1 over period is frequency. So that's why it ends up with 2 pi f. 2 pi f. 2 pi f, where f is the frequency. So, of course, we have to know also what is meant by frequency over here. So, T is time for one complete oscillation, one complete round. Okay, one complete round. And then frequency, maybe if you want to explain frequency, it is a bit hard sometimes. So now I write down for you. Frequency is actually the number of revolution. That means how many rounds the object takes per second. So that is the meaning of frequency. And remember, frequency is 1 over period. Okay, now let's see the next point. Relating angular velocity and linear velocity. So just now from here, when we have angular displacement, then there is linear displacement that come together, and their relationship is angular displacement multiplied with r radius, then you will get linear displacement. So they relate in that way. And likewise, when you have this omega, which is angular velocity, you multiply with r again, as what happened here, multiply with r to get the linear form. Okay, so the angular velocity multiply with r, then you will get the linear velocity. So this formula is very much related to this. Okay, so it's related. So V equal to R omega. Okay, so there is another way to take the formula. So where you have to understand it in this way. First of all, you have to see it from the basic, where linear velocity is linear displacement over time. Okay, so this is a very basic formula. Linear velocity is equal to linear displacement over time. And we know linear displacement, the S is actually r theta. Okay, from 1.1 just now, we already know S is r theta. So we can put S with r theta and we divide by t. And then we have theta over t. I separate them purposely so that theta over t become omega. And hence we get the formula V equal to R omega. Okay, so you have to know how to derive it as well. Okay, so let's see the next part. Okay, so we have how many formulas so far? We have 4. Okay, we have 4 formulas. The first one, S equal to R theta. The second one, omega equal to theta over T. And the application, 2 pi over T or 2 pi F. And the fourth one, V equal to R omega. So with 4 formula all together, let us apply it in this question. So if you look at this question, right, they said the drum of a spin dryer has a radius of 20 cm and rotates at 600 revolutions per minute. Okay, so show that the angular velocity is 63 radian per second. 63 radian per second. Okay, so you have to use angular velocity. Angular velocity. So where angular velocity is omega. Omega. So let's write down the formula first. Angular velocity is omega, which is theta over t. So we need to have information on how much time it spans for a particular angle. Okay, for a particular angle. So the information is given here. They give 600 revolution in 1 minute. Okay, in 1 minute. This is the information given. So what is the theta here? You know, when they make 1 round, the angle is 2 pi. So when they make 600 round, the theta is 600 times 2 pi. So this is the angle. And the time is 1 minute, which is 60 seconds. So we have the theta, we have the time, we put it into the formula, then we get the answer. So the theta is 600 times 2 pi. The time is 60. And then we just need to simplify it by using calculator. So we get 62.83. So I round off to 63 radian per second. And we managed to show it. Okay, so this is part A. Now part B, calculate for a point on the edge of the drum its linear velocity. So in order to find the linear velocity, so we think of the formula first. V equal to R omega. Okay, R omega. So where R is given here, 20 cm. 20 cm in meter, 0.2 meter. The omega is 63. Of course, to be accurate, let us use 62.83. Okay, so then we times. Then we get 12.6 meter per second. So this is one example on how we apply the formula. Okay, so let's move on. 1.3, circular motion. Okay, circular motion. Let's see the first point here. They say a body moving in a circle at a constant speed changes velocity since its direction changes. Thus, it is accelerating and hence experiences a force. So this is the introduction of the concept, why there is a force there, which is called centripetal force. Okay, why there is a force. Okay, so first of all, the body is moving in a circle and is moving at constant speed. So constant speed will make you think of constant speed means no acceleration, then no force. No force, you know, Newton's second law, right? F equal to ma. When there is no acceleration, then by right it has no force. But this statement is only true for linear motion, which means motion in a straight line. Okay, motion in a straight line, constant speed means no acceleration. No acceleration means no force. That is true in linear motion. But now it is motion in circle. Although the object is moving at constant speed, but because it's moving in circle, the direction is changing all the time. So how? Let's say I draw it up. You know, the circle is like this. So at one particular moment, the velocity is like this, or the direction is like that. And then at another particular moment, the direction is like this. So the direction is keep changing. And we have to know that velocity has two components, which is the magnitude as well as the direction. It is a vector quantity. So the magnitude is not changing because the statement here said it is a constant speed. But the direction is changing. As you can see, is this way and this way and this way. They keep changing its direction. So because of that, velocity is not a constant. Velocity is hence keep changing as well. So if velocity is changing, then there is an acceleration. Okay, that is an acceleration. So acceleration is, you see our basic formula. Acceleration is v minus u over t. So there is a change in acceleration. Then you have value for v minus u. And because of that, you have acceleration. So if you have acceleration, then you think of F equal to ma. So if you have acceleration, then you have force. So that's why there is a force, and we call it centripetal force. So what is centripetal force? We have to see it in this way. It is the resultant force. Resultant force is very important here. Resultant force. Acting on an object, moving in a circle, and always directed towards the center of the circle. Okay, so two important points here. The first point is resultant force. The second point is directed towards the center. Okay, these are the two important points. So how to take it? Let's say, for example, especially resultant force. We have to take resultant force in this way. Let's say you have a circular motion, a vertical circular motions, where the object is moving in circle, and there is a string that hold the object. There's a string. So if the object is here, then there is a weight, which is mg. And if a string is holding the circle, then there is a tension. So in this situation, the centripetal force, let's say I call it Fc. The centripetal force, which is the resultant force. And to count the resultant force, you have to take the fact that it is always directed towards the center. Always directed towards the center. So because of that, we take towards the center as positive direction. So T is positive, and hence mg is negative. So the resultant force is obtained by using T minus mg. So you take T minus mg, you get the resultant force. That resultant force is the centripetal force. And the centripetal force is acting towards the center of circle. Okay, so let's say another example. If you have your object here, in a circular motion, the object will reach here at one particular moment. So when that happens, okay, so imagine that the string is still holding the object. So there is tension downwards, and mg is also downward. Mg is also downward, the weight of the object. So now both of the forces that act on the object is downward. And because of that, you want to count the centripetal force, always remember it is the resultant force. And always remember another thing, we take, because centripetal force always directed towards the center of the circle, so we take the direction that act towards the center of the circle as positive direction. In this case, downward is positive. Downward is positive, and both forces here are downward, so they are positive. So we have T plus mg, both are positive, so we just add them up, and that is the centripetal force. So the centripetal force is hence greater on top, and the centripetal force is lesser at the bottom. Okay, so that is how we count centripetal force. So we have many other scenario also actually. So let's say another example. This is example 1, let's say, about centripetal force. So now example 2. Sometimes you don't hang your object in this way, you hang it purposely in, let's say, imagine this is the ceiling. So there is a string, the object is here, and you just swing it until it moves in a circular path in this way, like a cone shape. So the circular path is in this way. So if it's in this way, how to find centripetal force? So let's take a look also. Okay, so first of all, this is the center of the circle, and let's say they make an angle of theta here. Theta, the tension of the string is here, mg is downwards. Okay, so in this case, how to find the resultant force that act towards the center of the circle? Okay, so you have to know towards the center of the circle is towards here. Okay, from here to here, to the center of circle. So we have to find the force over here. So to find the force over here, first of all, you need to know for the weight mg, right, which is perpendicular to the direction which acts towards the center of circle. When they are perpendicular, right, the weight will not contribute any value to this direction. Okay, remember, when it is perpendicular, it doesn't contribute any value to the direction which acts toward the center of the circle. Okay, perpendicular, no, but this one, yes. This is not perpendicular. This one take a particular angle, which is not 90 degrees. So it will contribute some value to this direction, towards the center of the circle. And to find this, we just use some trigonometry. Sine is opposite over hypotenuse. So let's say I write down sine theta is opposite, let's say I call it x, over hypotenuse is t. Okay, we are considering the right angle triangle over there, and after that we get x equal to t sine theta. So this is the, okay, I put it in blue, this is the component of the tension that act towards the center of the circle, and the value is t sine theta. So this is the value that contribute to the centripetal force, and hence centripetal force is equal to T sine theta. So which is the resultant force again? So the resultant force is T sine theta. For this case, the mg doesn't contribute any value because it is perpendicular to the direction that acts towards the center of the circle. Okay. One more example. This one, centripetal force is the important part. Okay, so we have to take more example. Okay, so to see another example, I had to draw out a diagram like this. Let's say I have a circular disc. Okay, circular disc, and It's a rough circular disc and it's rotating. Okay, rotating. So this is the center of circle. The disc is rotating, rough surface, and you put a mud here. So you put a mud here. Okay, I write down mud on a rough surface. On a rough surface. So when we say it's a rough surface, that means it has frictional force. It has frictional force. So what happened is, okay, let's say I label this is the mud. The mud is on a rough surface. So the disc is spinning. So the disc is spinning. You know, when the disc is spinning, the mud has a tendency to be thrown away from the, thrown away from the disc. Thrown away. There is a tendency to be thrown away. So the motion is, thrown away means the motion is away from the circle. The motion is here. There is a tendency to be thrown away from the circular disc. But if the frictional force, is a rough surface, right? So if the frictional force is managed to hold the mud, and then the mud will remain on the disc. So what am I trying to say is, if the motion is acting outward, then the frictional force is acting inward. So I call it FF, frictional force. It's acting inward. And this frictional force is the force that acts towards the center of the circle, and hence this contribute to the centripetal force. Okay, so again, you have to forget about mg, because mg acts downwards. Mg acts downward, which is perpendicular to the center of the circle. Okay, so we can just forget about that, and hence centripetal force is due to the frictional force. Due to the frictional force, FF. Okay, so FF, and of course, you know, frictional force is mu times R. Mu times R. So the coefficient of frictions multiply with the normal reaction. So this is another way to see the centripetal force in a more complicated situation. Okay, so I already give 3 examples for centripetal force. Now let's move on. Let's see the formula. So centripetal force, as you can see over here, centripetal force is mv square over r. Mv square over r. Centripetal force is also mr omega square. Mr omega square. Okay, so which means when they give you this formula, then are we still going to use all this t plus mg, t minus mg, or t sine theta, or this one mu r is the centripetal force? Actually, we have to use it together. We have to use it together. For example, right? Let's say, okay, I put it in black color. Let's say, when you know our formula is mv square over r and mr omega square, and at the same time, we also know it can be t minus mg at this position, and then we can form an equation like this. We can form, let's say, for example, example, I put in black. Example, we can let mr omega square equal to t minus mg for this case, and then we can find out omega, for example. So you can find out the angular velocity. Okay, you can find out the angular velocity. And likewise, mr omega square equal to t plus mg. And then we can find out omega if necessary, if the question is asking that. So it is possible to find it out. So that is how we apply it. We can let the centripetal force formula equal to the resultant force that we obtain. Okay, so just keep in mind, and of course you will see past year paper afterwards to understand more. Okay, now the next one, centripetal acceleration, derived by equating Newton's second law and centripetal force. So what is Newton's second law again? It is actually F equal to ma. F equal to ma. And then you know, you equate F equal to ma with the centripetal force formula up there. So you will get something like this. mv squared over r equal to ma. You got the m on both sides. Then you get a equal to v squared over r. So you get the formula of the centripetal acceleration. Okay, so that is one form. Of course, to get a equal to r omega squared, right, we have to let mr omega squared equal to ma. Then you cut the m on both sides. Then we get a equal to r omega squared. Okay, so we get the formula. So yeah, these are the two formula that we get. A equal to r omega squared and a equal to v squared over r. Okay, so these are the two formula. Okay, so settle for this page.